Okay, thank goodness. Welcome back, guys. This is our final little lesson for MAC2312. I'm sad that we couldn't have this particular one be a live one, but sometimes schedules work out that way. So that's where we are. I'm going to show you here how to find some areas in Forth and practice a little bit more with that stuff. Just trying to make sure everybody's comfy with the new material. I know that a sizable chunk of people are still thinking about working on some power series stuff earlier this week, so I'm hoping that this helps tie things up for those folks who kind of this is of course just switched over MAC 312 section 4. It's a lecture extra. I don't know. I want to say like lecture 2, but it was something else now. So yeah, it's that one on the 22nd. Lecture redux. Supplemental. Here, we're going to talk a little bit more about graphing and polar coordinates. Because I know nobody remembers it from trigonometry. We're going to talk a little bit about finding areas in polar coordinates. And then we're going to talk about some fun stuff. I'm going to show you how to take a natural log of. Let's do it. Let's do some polar graphing. I showed you a few examples earlier today, like so the examples r equals a constant. This is a circle. Radius r, centered at the origin. In polar coordinates, sometimes they call the origin the pole. You can call it the origin if you want. You can call it the pole too. And the other kind of silly example we looked at was theta equals a constant. And this is a line through the origin of the pole, making angle k radians with the polar axis. So we have to make a picture. Circle is what it sounds like. The radius is k. Those are the graphs. I want to show you some more sophisticated stuff. We also looked at a spiral, Archimedean spiral, but I want to show you some more kind of sophisticated methods for graphing besides making tables, right? That's what we did there. We made tables, let's be honest, right? We just, like you were in algebra class, we made a table for r and a table, a table with r and theta, and we computed it. And we plotted, points and connected the dots like we're in 8th grade. Some more sophisticated methods involve understanding what it means to go from Cartesian to polar coordinates. We call it a coordinate transform, and we want you to start being able to try to picture those coordinate transforms. So how I'm going to show you to graph the remaining examples is by graphing them first in Cartesian coordinates, graphing them on a regular kind of rectangular coordinate system, and then transferring that graph over one piece at a time into the polar coordinate system, acknowledging what it does to the shape. All right. How about cos theta? Let's sketch r equals cos theta in polar coordinates. Like I said, first we're going to sketch it in rectangular coordinates. The graph paper is useful for this, I don't mind. Always sketch your thing with domain at least 0 to 2 pi. So theta is going to be our independent variable. And r is going to be our dependent variable. So I'll call this -1. It's +1. I'll call this 2 pi. It's halfway there. It's pi. And halfway there. It's pi 2. Halfway between these guys. Space. I'm not sure. Yeah, it was 3 pi over 2. So we all know what cos theta looks like. Oops. Cos of 0 is 1. Cos of pi over 2 is 0. Cos of pi is -1. Cos of 3 pi over 2 is back to 0. And cos of 2 pi is +1. So the cosine curve. It's like this. At least from 0 to 2 pi. This is the rectangular coordinate sketch. And you always start with this. You're trying to graph something in polar coordinates, sketch it first in rectangular coordinates. Then you transfer that into a polar graph. Polar coordinate graph. Here's my polar axis. And we can think of that as being like an x and y axis. There's no harm in that. I'll show you guys. Ooh, looks like I'm about to get kicked out. All right. Hold on, I think my internet service is dying. I still appear to have a connection, baby love. Let me see. No, my shit just hadn't figured out that it lost its connection yet. Yeah, mine. Oh, no, I'm still here. Somehow. That's funny. Yeah, no, I'm still working, baby. I still can ping Google and stuff. It's just real slow. All right, sorry about that, guys. Looks like I haven't lost you. I was expecting to lose you there. My internet's been going in and out. I've been consuming to record these. It's been a nightmare. Anyway. This serves as your table, right? This is actually better than your table. It has the ordered pairs. It has the information you want, but it has also the information from infinitely many other points, because you got the whole curve. So this is actually much superior to the table for graphing in polar coordinates. It carries the same information and then some. So when theta is equal to 0, r is equal to 1. Let me mark this as 1 on my polar axis. Here's the polar point, 1, 0. R equals 1, theta equals 0. We always put r first. When theta is pi over 2, r has come all the way back to 0. So think of this as a little arm rotating around, and a little guy running in and out along the arm as it rotates. And that little guy leaves a trail as he goes. This graph tells you how far out the little guy is as a function of the angle that you've rotated. That's it, right? It's your theta r graph. It's just in rectangular coordinates. So if you want to figure out how to move this into polar coordinates, imagine this little guy out here. Right now, his distance out on this arm is 1, because when theta is 0, r is 1. If I rotate up a little bit, he will start to come in, because this graph is decreasing here. So as I rotate up a little bit, my r value runs in a little bit. And as I rotate more and more and more, he's coming all the way into 0. Ignore this dot. This is me being foolish. But as theta comes up to pi over 2, r decreases to 0. So my little guy runs from distance 1 out here all the way into distance 0. You can plot some other points along the way if you wanted, like pi over 4. You know, r here is root 2 over 2. It's like we calculated that as a decimal earlier. Just to get a feel for it. It's 1 over root 2. .7. So like 0.7, and then you rotate it up pi over 4. It's like here. And you can keep going. By the time you get back to pi over 2, though, you got to be back over here, right? So the curve you actually trace through that part looks like this. This little piece here corresponds to this part of the polar graph. And now, as you rotate past pi over 2, your little guy, his radius is negative. Remember I told you I like to think of negative radii here as reflecting over the origin. This is why. Because as I rotate just a little bit past pi over 2, my radius is no longer 0. It's like negative now. It's going towards -1. So normally if my radius was going out towards +1, my little guy would be running out in this direction, out along my arm as it rotates around, remember. But it's negative. So rather, my little guy is running around on the other side over here, reflected through the origin. So as I rotate just a little bit past pi over 2, he comes out. And like 3 pi over 4, he's like here. And then by pi, he's all the way out at -1. So what I'm getting from this portion of the curve is a piece that looks like this. And this thing is what it looks like. It's a circle. The circle here is centered at the Cartesian point, and it happens to be the same polar coordinates. So I guess I can write it unambiguously as 1, 0. That's whether you want to think of that as x, y, or r, theta. I'm sorry, 1/2, 0. And the radius is 1/2. Right, that's the polar graph of r equals cos theta. R equals sine theta is similar. Give you some perspective. Just being rough about it. Sine theta looks like this from 0 to 2 pi. So this is the rectangular graph and the polar graph. And this is 1. We start out at 0, 0. When theta is 0, this is my theta axis, this is my r axis. When theta is 0, r is 0. If I rotate up a little bit, my r value starts to book out. Again, you could check like pi over 4, you get root 2 over 2, so it's like 0.7, so pi over 4, we're at like 0.7. So it'd be like somewhere around here. By the time we rotate up to pi over, by the time we rotate up to pi over 2, rotate all the way up to pi over 2 here, our radius has come all the way out to 1. So we're going to be like up here. As we rotate past pi over 2 towards like 3 pi over 4, our radius starts to come back in. So kind of picture this. I start out at the origin. My dude's walking out, walking out, walking out, hits that first dot. Walking out, walking out, walking out, walking out, hits that second dot. And I continue to rotate around. And I'm just a little bit past pi over 2. So I'm like right here on this graph. My little guy is walking in, walking in, walking in, walking in. And 3 pi over 4, I would hit a dot parallel to that one over there. And then at pi, by the time I walk all the way back around to pi, I'm back to the origin. So really just from 0 to pi, both of these guys sketch that circle. And if you run through this again, it'll sketch the circle again. So you actually get your whole circle from this part. Just like on the cosine graph, you got your whole circle before by like a half period. But this is going to trace it again. As you rotate past pi, the little dude's going to run out, but he's going to be running out in the negative direction. So he'll be like over here again, over here, here again. And as you rotate a little bit more, by 3 pi over 2, he should be down here if r was positive, but r is negative, so he's going to be up there. And you really do just trace that circle down. There's lots of fun things like this that I could show you. Again, here you have a circle. The center this time is everything's just moved up, like rotated over 90 degrees. Center here is at 0, 1/2, and the radius is 1/2. Those are Cartesian coordinates. All right. I think we need to do something like r equals. Let me grab an example from your book. Cardioid or I don't actually see the examples I'm looking for. Maybe they are in the next section. 2 cos theta, 1 plus sine theta, sure. Why not? Oh. We want to sketch it. All right, that's the idea. So in rectangular coordinates, 1 plus sine theta is like regular sine theta, but bumped up 1. So here's y equals 1. I'm going to add this. This is like an equilibrium for this sine wave. Remember how this works, right? You take the regular sine wave of amplitude 1, you bump it up 1. So its max is out here at 2. Its min is down here at 0. Sine starts. And so his adventures at the origin. But now that that's bumped up, he's going to start his adventures here. By pi over 2, he will reach his max of 2. By pi, he will reach his, by pi, he will reach what would normally be 0 for sine, but since it's bumped up 1, it will be 1. By 3 pi over 2, when sine of theta is negative 1, we'll have an actual x-intercept. And then over here. So here's our sine wave. And we can transfer this over into polar coordinates, just like we've done for the rest of these. It's going to look like this. When theta is 0, r is 1. So we measure this as 1, this 2. When theta is 0, r is equal to 1. Right? This is my theta r graph. Theta here, r here. So theta 0, r is 1. As theta increases to pi over 2, r exceeds 1, goes out to 2. So this point, I don't know. Here, the polar point here, which is 2, comma, remember these are always r, comma, theta. By the time we rotate around to pi, we're back to 1. Interesting. All right, seems that my connection dropped. I'll try to edit this. But we're back. So 1 comma pi over here. Try to follow this. My little dude starts out here. I have some more pen to work with. At radius 1, as I rotate up, my little dude walks out further and further. And then my little dude is going to start walking in as I rotate back, but only back to 1. So in fact, what we're doing here is something like this. And now as we rotate past pi, as we go past pi here, towards like 3 pi over 4, right here, my radius is coming in. At 3 pi over 4, we would be at 1 minus root 2 over 2, which is like 0.3. And then by the time we're reaching 3 pi over 2, by the time my arm is all the way down here, right, so we rotate through like this. We go all the way from 1 out here down to 0.3 here. And by the time we come into 3 pi over 2, we're at 0. And then we pop out symmetrically. So this is the shape. This is called a cardioid. Because if you, the orientation like this, if you turn it over, it looks like a heart. Looks like a heart. So they call it cardioid. There's other things like this, limosons. I should do one of those. Or maybe I'll just show you the area thing. So I've shown you how to do this. We'll do one more real quick and I'll show you this. 1 plus 2 plus 3. Pretty sure that'll be a limison. And rectangular coordinates. It's 1. So it's like -1, it's 2, it's 1. Again, this guy has been shifted up. This is a cosine wave of amplitude 2. It's been shifted up 1 unit. So he's going to start up here. That's 2 pi. That's 5. That's 3 pi over 2. He starts out at the top of his amplitude, 5 pi over 2. He comes into the this piece being 0, which means we're at 1. And then by pi, he's going to bottom out at the bottom of his amplitude. Since his kind of equilibrium is at 1 and his amplitude is 2, bottoming out at the bottom of his amplitude means he's down here at -1. And then he's going to come back up to his equilibrium by 3 pi over 2. And it's going to finish out at the top of its amplitude. So here's my cosine. Looks like this. Amplitude 2, equilibrium is up there at 1. That's it. So if you want to translate this into polar coordinates, this will be the last example. I'll call this one, this 2, 6. We're starting out when theta is 0, r is 2. when theta is pi over 2, r is 1. So that's right here, right? Now you go out 1 and you rotate up pi over 2. When theta is pi, we're like negative. Something weird happens in here. So this, whatever this theta value is, where this goes from positive to negative, something strange happens. It's definitely just past pi over 2. We can figure out where it is. So we can solve the equation r equals 0. That means 1 plus 2 cos theta would be equal to 0. And that means cos theta is negative 1/2. So the theta values here that solve cos theta equals negative 1/2, we know from the unit circle. That's 2 pi over 3. And then what do you have? 3 pi over 3, that's pi. 4 pi over 3, that's 60 degrees to the next quadrant. So 4 pi over 3, right? That's our next guy. So that's these two values. This is 2 pi over 3, and this is 4 pi over 3. So at 2 pi over 3, this thing comes back into the origin. So as we rotate past pi over 2 towards 2 pi over 3, my little guy is running in. So just to be clear, so far we have this. And now as I rotate a little bit past 2 pi over 3, my radius should come poking back out, but uh-oh, it's negative. So instead of going out this way, it's going to go out this way. And it's going to come out to a max of negative 1. So the polar point negative 1 comma pi, remember, is actually this point. So what's going on is something like this. Strange. So we're right here at the point negative 1 comma pi, the polar point negative 1 comma pi. Either you can come out negative 1 and rotate around pi, or you can find the point 1 comma pi by coming out 1 and rotating around pi, and then reflect through the origin. That's what I've been doing here. So far we have this. You might notice that there's a lot of symmetry to this graph. So you can expect that this will finish up in a symmetrical way, and it does. But beyond that, you can just follow the points like we've been doing. So if you continue to rotate a little bit, you see that r starts coming in from negative 1 back towards 0. And by the time we get to 4 pi over 3, which would be like here, we're back into 0. So I'm going to come back in like this. And then as we rotate past 4 pi over 3, we continue this rotation into this quadrant. R grows. When theta is equal to 3 pi over 2, that's straight down. R is negative 1, or sorry, R is positive 1 again. And then it comes back out to 2 as we rotate around. These are called limicons. All right, that's enough graphing in polar coordinates. I promised you an explanation for that area formula. And then I'll let you go. So. Phone call here. So if I have a polar curve here, whatever, something like this, and I want to find the area bounded by this curve in the following sense. Like I want to find the area bounded from this angle here, alpha, to this angle here, beta. Talking about a kind of wedge-shaped area. Are you texting with Penny or anything right now, baby? Okay. I think my dad just tried to call me, but I didn't want to interrupt this thing. Okay. So this is the area we're after. This curve is, r equals r of theta. Or you can call it f of theta. I'm just going to use this notation. But the textbook does this. Doesn't matter. Same thing. Then the area here, the shaded area here, is the integral from alpha to beta of 1/2 r of theta squared d theta. The reason for this, I can try to explain. It's not terribly hard. It mostly comes from this idea of the area of a sector of a circle. So you need to know that. I'm going to redraw this picture here. Something like this. There's my alpha. And here's theta. Again, the curve here is, r of theta. The place that integral formula comes from, you can build a Riemann sum out of these things. You chop it up into little wedges. Each one of a kind of angular thickness delta theta. So I'm going to yell at my dog. Hamlet, no Bubba. So each one of these guys is a little angle delta theta. They're all the same. They're all delta theta. So it's like partitioning the angle interval alpha beta into subintervals. And then you treat each one of these things as a little sector of a circle. So you approximate each of these parts, areas, by pretending like they're sectors of circles of that radius. What radius? Well, the radius from the right endpoint of each one of those subintervals. So this would be like r of alpha, which is, you could call theta 0. This would be r of theta 1, r of theta 2, r of theta 3, and so on to r of theta n minus 1, and then theta n. There's left in place. Okay, that's fine. And here, theta n would be also beta. Something like this. And through this mechanism of the area of a sector of a circle, you know what that is, I actually prove this for you in the little complete the square review that's up on Canvas. Area of a sector of a circle with radius r is 1/2 theta r squared. Just one way to think of it. It's also a linear, it has to be a linear function of theta that gives the proper area when theta is equal to 2 pi. So if you plug 2 pi in here, you get pi r squared, as you should, the area of a full circle. That's one way to think of it too. It has to be linear in theta. It has to be 0 when theta is 0, and it has to be equal to pi r squared when theta is 2 pi. So each one of these little guys, I call each of these areas like A1, A2, A3, AN-1, and AN. Then the exact area can be approximated as the sum from I equals 1 to n of the little areas. Each of those little areas, remember, has an angle inside delta theta. So according to my formula for the area of a sector of a circle, each one of these little areas is delta theta, right? The little angle inside delta theta times the radius there. So this is 1/2 delta theta times the radius there squared. So this is r of I squared. And we can rewrite that as I'm leaving the 1/2 inside the integral. So I'll put it sigma I equals 1 to n 1/2 of theta I squared delta theta. And this should scream Riemann sum. It does. It is. Which means the exact area is straight up equal to the limit as n goes to infinity of this thing, sigma I from 1/2 r of theta I squared delta theta, which is the integral of theta of 1/2 r of theta squared d theta, like I said. That's where it comes from. Quick application or two, and then I'll let you guys go, okay? Because these are not hard computations. Square the function r, multiply by 1/2, do the integral. So the example first, how about the unit circle? Where r equals 1, that's the unit circle. So the area is the integral from, well, theta here is 0. We got to go all the way out to 2 pi. So this is the integral of 0 to 2 pi. 1/2 r of theta squared. That's integral of 0 to 2 pi. 1/2 1 squared. Because r here, the function r is just the constant 1. So of course that's 1/2 theta divided from 0 to 2 pi. That's 1/2 times 2 pi minus 1/2 times 0, which is 0. So this is just pi. And we know that that's the area of the unit circle. Area is pi squared. Right? Okay. One more complicated example. Here's a fun one. Sine 2 theta. There's an extra sneaky graphing problem built in here. Rectangular graph here, sine 2 theta, this isn't any alteration to amplitude, it's alteration of frequency. So from 0 to 2 pi, sine 2 theta, his period is just pi. So he's going to go through 2 oscillations between 0 and 2 pi. Here's pi over 2. We'll get this pi over 4, 3 pi over 4, 3 pi over 2, 4 multiples. From 0 to pi, we got to run through a whole period of sine. So this is what we're looking at. And then from pi to 2 pi, we've got to run through a whole other period for sine. Oh, sorry. So there it is. That's sine of 2 theta graphed from 0 to 2 pi. So everyone how to find the period. It's always 2 pi over like this number. It's omega. It's the angular frequency. This is the period of sine omega cos. I want to transform this into polar coordinates. Something funky happens. It's a lot of fun. this as 1. From 0 to pi over 4, this thing pokes all the way out from r equals 0 here. And then by the time we swing up to pi over 4, we're out to 1. So what we're doing here is we're doing something like this. Sorry, we're doing something. So 0, by the time we're at pi over 4, we're out to 1. So we're doing something like this. And then as we come from pi over 4 towards pi over 2, we dive back into the origin. Our radius is going back to 0. So here we are at like pi over 2. I think of this thing as rotating. And then from pi over 2 to pi, where normally we would be drawing over here because we're negative, will be reflected in drawing over here. From just pi over 2 to 3 pi over 4, we're going to poke out of the origin and come back out to like a radius of 1. And then 3 pi over 4 is normally over here, but we're reflected, so we're over here. And then from 3 pi over 4 back to pi, we come back in. Now we're at this part. So the extra bold portion here actually drew the extra bold portion here. And that's surprising. But it's because r is negative. Normally from theta equals pi over 2 to pi, we would be drawing in quadrant 2. But because r is negative, we're reflected over here into quadrant 4. But then as we come past pi, r is positive again. So I'll be drawing in quadrant 3. And this bloop here is going to give me a symmetric bloop here like you think it will. And then from 3 pi over 2 to 2 pi, we would normally be drawing over here, but because we're negative again, we'll be reflected. So we do create the symmetric piece over here. And that's this. These are called petal graphs. And I'm going to find the area of one of those loops. This first loop was created as theta went from 0 to pi over 4 to pi over 2. So if I go after this area, that would be the integral from theta equals 0 to theta equals pi over 2 of 1/2 times my r function squared. Now r here is sine of 2 theta. So this is sine of 2 theta all squared to theta, which is 1/2 integral 0 to pi over 2 sine squared 2 theta d theta. And this is an even power of the sine function, so we integrate it absent an odd power of cosine. We integrate it using half-angle identities. So this would be 1/2 times 1 minus cos of, this is already a 2 theta here, so this is going to be a 4 theta. 3 theta. And now we're good to go. I can pop this 1/2 out, I get a 1/4. Antiderivative for 1 is just theta. Antiderivative for 1 is just theta. 1/2 came out, that's the 1/4. Antiderivative for cos 4 theta is sine 4 theta over 4. It's a little micro u sub. You remember those from exam 1. And we evaluate this apparatus from 0 to pi over 2. When theta is 0, everything's 0, right? 0 minus the sine of 0 over 4. That's 0 minus 0. When theta is pi over 2, I do get something. I get 1/4 times pi over 2 minus the sine of 4 pi over 2. Well, 4 times pi over 2, that's 2 pi. Uh-oh. That's 0 again, isn't it? So I just get 1/4 times pi over 2 because sine of 2 pi is 0. So it's pi over 8. That breaks that area. And that's all I have for you guys as far as coursework is concerned. I do have something else I want to show you. But it's getting quite late here, and I can't trust my internet to not go out. So I'm going to go ahead and cut this off now. And then I'll share the other stuff with you in a separate video.